Hello. This next video covers motion in multiple dimensions, analyzing dynamics problems in multiple dimensions, including ramps. So first, section 4.3 just introduces F equals ma in 2 dimensions, and then 4.5 will look in detail about ramps. Okay, we're quickly going to come back to this problem, but just a sort of 1-minute summary of this first section is that F equals ma is a vector equation. So sum of the forces, which are vectors, is mass times acceleration, which is a vector. Is a vector equation. So what this means is that when you draw a free body diagram, so say you have an object and you draw some forces on it. Say one here, one here, one here. That's it. The strategy that you want to do, so the first thing you do is pick an object to analyze and draw a free body diagram. All right, so suppose we've already done that. So we picked an object to analyze, we drew all the forces acting on that object. The second thing to do is to choose a coordinate system So in general, what you want to do is take a look at the free body diagram and choose your x and y axes to line up with as many forces as possible. So here, all the forces are horizontal and vertical. So it looks like our standard x direction being to the right and y direction being up is probably a good choice. Right? Because all of the forces are either in the plus x direction or the plus or minus y direction. So the third thing to do is to apply F equals ma to each component separately, to each component. Okay, so this section is all about this third step. We got a little bit of practice with step 1. Step 2 is just in preparation for step 3. Okay, so what this means is that F equals ma is actually multiple equations packed into one. All right, so you could focus on the x direction, and what this means is the sum of the x components of all the forces equal to mass times the x component of the acceleration. And the sum of the y components of the forces is mass times ay. If we were dealing with a 3-dimensional problem, we would also have sum of the forces in the z direction is m times az. Okay, so it's important to realize that Newton's second law as a vector equation is multiple different equations for the different directions. And so your book covers this pretty succinctly, just like this: fx equals max, fy equals may. But realize that the acceleration, there's only one acceleration. There could be multiple forces. So the left-hand sides of this, it would be preferable if your author put sum of all the forces, sum of all the x components. Okay, so we're going to use this strategy to analyze this problem right here. So we have a person pushing a book against a wall. The person's pushing horizontally to the right. And because of static friction, so we're allowed to use this coefficient of friction right here, because of static friction, the book can actually stay at rest, remain at rest against the wall. And what is the minimum horizontal force required to keep the book at rest against the wall, is the question. Okay, so let's look at that. And then after we answer this question, we'll be able to analyze ramps, also using this strategy. Okay. So, original problem. So step 1, pick an object. Our object is going to be the book. Okay, we're going to need to look at, we're interested in the book not moving, not the person not moving. We're interested in the book not moving. And all of the relevant forces are against the book. It's the applied force against the book. It's the static frictional force on the book, the weight of the book, etc. And I suppose, let's assume the book has mass m. We'll need to know that for our answer. Okay, so our object is the book. Now we need to pick an object, or well, we already picked an object. We need to draw the free body diagram. Okay. Well, I guess that's probably step one. Okay, so our free body diagram, I think the book was red in the picture. Our free body diagram, well, weight is probably the easiest thing to draw. That one's always on there, mg. So you're allowed to turn your brain off for weight. That's always going to be vertically downwards like this. However, you have to turn your brain back on at this point. You can't just say the normal force is upward. This is not true for this problem. On a horizontal surface, you can do this, but here the surface is vertical. So because the wall is right here, the wall is pushing in the normal direction, normal away from the wall. So there's an applied force from the person towards the wall, it's pushing the book against the wall, and then the wall responds with this normal force. Okay, now remember from the last video on friction, the way to analyze friction is to first write all of the other forces acting first, pretend friction isn't there. So if friction's not here, the book would fall down. Okay, but friction is going to try to oppose the motion. Right? And here we're told we have static friction. So we're gonna have the static frictional force keeping the book in place. So it's this normal force that allows a static frictional force to point upward. Right? So our object is the book, and we drew the free body diagram. Now the second piece is to choose a coordinate system. So the second part of our strategy, choose a coordinate system. And here it looks like all of our forces are horizontal or vertical, so why don't we just choose our standard plus x and plus y. So you might think that you're always going to do this, horizontal and vertical, but when we talk about ramps, we're actually going to choose a different direction. So stay tuned for a different coordinate system. Now the third piece is to apply Newton's second law to each component. So what this means is that the horizontal pieces, so the sum of the fx's, well, it looks like, so the two vertical forces have 0 x component. So this one and this one are going to be 0 for this equation. F applied is in the positive x direction, so the x component of F applied is positive. And the magnitude of this force is n, the normal force, but it's in the negative x direction. So the x component of the normal force is negative n. Sum of those forces is equal to mass times ax. And we're told in the problem that the acceleration is 0. So what this means is that ax is 0 and ay is 0. So if you know that an object is at rest and staying at rest, you know every component of its acceleration is 0. Right, so this is 0. And then similar for the y direction. Here the frictional force is in the positive y direction and the weight is in the negative y direction. So sum of those two is equal to 0. Okay. So this is the general strategy. Notice how we haven't yet answered the question, but this is at least how we're going to translate our free body diagram, our picture of what's going on, into equations. Right? The rest of it is just manipulating the equations based on what we know about the problem. Now the problem says, what is the minimum horizontal force required to keep the book at rest against the wall? So we're requiring that the book does not move. Notice how we haven't yet thrown in the coefficient of friction, right? So that's going to appear in the maximum amount of static friction that's possible. Okay, so let's rearrange these equations actually. So first of all, so looking at the first equation, we have the normal force is equal to the applied force, right? That's what the horizontal direction is saying. And then the vertical direction is saying that the static frictional force has to be equal to the weight in order to keep this book not moving, not accelerating downwards. So what we know about static friction is the following. Static frictional force has to be less than or equal to the maximum amount of static friction, which is mu sub s times the normal force. Now, we were given the mass in the problem, and we're going to involve, the question is asking about F applied, but we weren't given, and we don't need to know anything about the normal force, so we're going to get rid of the normal force. here. And the static frictional force, we're going to go ahead and plug that in. We weren't asked about the static frictional force. We're going to have to relate F applied to the mass. So we prefer, in other words, in these two equations right here, we prefer the variables on the right-hand side versus the ones on the left-hand side. So let's do this. Okay, we have mg. Fs is equal to mg. This is going to be less than or equal to mu sub s times the normal force, F applied. Or in other words, F applied has to be greater than or equal to, so notice how this side is greater than or equal to the left-hand side. F applied is greater than or equal to mg over mu sub s. All right. So most of the time, a realistic value of mu sub s is not greater than 1. It can be, but most of them are less than 1. Like 0.5 is a more typical example of a book against a wall. So you probably know this from experience. The easier way to hold up a book is just to provide a vertically upwards force, mg, to counteract the gravitational force directly. If you're going to press the book against the wall and hold it up, you'd have to push harder than you would otherwise have to pull it up. So in other words, mg divided by 0.5 is 2 mg. So you would have to push twice as hard as you would have to pull up on the book in order to keep it from falling. But it is possible, which is interesting. I mean, you're pushing in the horizontal direction, and then that wall sort of indirectly turns that into a, via friction, it indirectly turns that into a vertical force, which is kind of interesting. So yeah, this is a problem involving friction from last time, but you see the importance of keeping track of directions. The normal force is normal to a surface. It can be horizontal, doesn't always have to be vertical. It's just perpendicular to the surface. Okay. All right. So that's the gist of this section. Just keeping track of the directions and using all of them separately to answer problems. All right. Inclined planes is the next topic. And the author of your textbook says that it's not a terribly interesting problem, but it's in his words, it's your entry ticket into the business. You have to be able to analyze these problems to progress in physics. So even though the problem might not be terribly interesting to you, it has you use some of these skills of decomposing vectors into components. Using your models of friction and Newton's second law to turn that into analytical, or maybe I should say quantitative statements and predictions about how quickly a mass might accelerate. So this is good practice for skills that we're going to need throughout physics, right? Regardless of how antiquated the topic might seem. All right, inclined ramps, inclined planes / ramps. So the general setup is we have a ramp that's at some angle theta relative to the horizontal, and we have a block on it, like this. It's a block of mass m. So automatically we know that there's a gravitational force. That's like the easiest force we always know exists there. So there's a gravitational force. I'm drawing my free body diagram directly on this diagram. So the black ramp is just sort of the background, but the red arrows are the actual forces here. So there's a gravitational force, mg, vertically downwards. There's a normal force that's normal. Remember, the word normal means perpendicular. So there's a normal force that's perpendicular to the ramp. And that's not exactly in the vertical direction. Right? So if mg is vertically downwards, the normal force is not vertically upwards. It's perpendicular to the ramp, in the direction away from the ramp. So if there's no friction, this is it. But in the case that there is a frictional force, remember the frictional force, we first analyze all the forces without friction. The mass is going to fall down the ramp. It's It's going to go down the ramp, and so friction is going to oppose this motion. So frictional force this way, if it's non-zero. Okay. So, so this is your first exposure to a problem where it's actually easiest to introduce a coordinate system that's not just vertically upwards and horizontal to the right, but actually along the ramp and perpendicular to the ramp. So the normal force is going to be what we're calling the y direction, is pointing in the y direction. And then the direction down the ramp is going to be the x direction. So the normal force is just in the y direction, the frictional force is in the minus x direction. But this means that gravity doesn't point nicely in either one of these two. There's a component of gravity along that positive x direction, and there's a component of gravity along the negative y direction. Okay, so gravity you could think of as the sum of two different vectors, one along the x direction, one along the negative y direction. So mg is like the hypotenuse of this right triangle. Right? We are decomposing or resolving the gravitational force into its two different components. Okay, and I drew the arrows for vector components. Okay, so we need to figure out how big these two components are. Okay, so right now I'll just call it A and B. Right? But the question we're going to answer here is how big, what are the magnitudes, what are A and B? So you'll get pretty quick at this and you'll be able to figure out what A and B are automatically. But in the meantime, you might have to be good at drawing careful diagrams. So you can't just scribble something and you know, if I look at a student's work and it looks like this, it's like I can't read that. So just keep in mind, if your scratch work looks like this, you know, you're not helping yourself. It's going to be very hard to read anything like that. All right, so let's be careful with the right angles. Let's try and mark up this triangle. In other words, we have this angle theta. So let me redraw this. So this is our ramp, and that wasn't straight enough. So let's try and get a straight line. That's close enough. This is our angle theta. So our ramp is in black, and then our gravitational force is going to be this one right here in red. Right. So let's decompose it into the horizontal piece and the vertical piece. So let's see this. So we have a bunch of right angles here. Let's bring that a little closer. Okay, this is a right angle. So this angle theta is the same thing as, so let me draw another horizontal line here. This angle is theta. Does everyone see that? This we have a horizontal line right here. So by the way, I'm using horizontal and vertical like this, and then I'll also have the x and y directions, which what I wrote right here. So horizontal, vertical, x and y are different directions. So this horizontal direction and this horizontal direction are parallel, and then the ramp, this line right here crosses both of those horizontal lines. So these are alternate interior angles right here. So this is theta. That means that this one right here is the complement of theta. Let me clean up this diagram. So this is theta. This is the complement of theta. Call it maybe alpha or something. And then this is theta right here. Okay. So you can already see how ugly this diagram is. So this is why you kind of want to be careful with your triangles here. So if this is MG, this is the hypotenuse of our right triangle, where our angle theta is down here. Okay, so we called it A and B. So we're trying to figure out what A and B are. Sine theta, I'm looking at this angle right here. So sine of theta is opposite over hypotenuse. So this is A over mg. Or in other words, A is mg sine theta. Similarly, cosine theta is adjacent over the hypotenuse. So this is B over mg. Or in other words, B is mg cosine theta. As long as your angle, theta, is measured relative to the horizontal, then the component of gravity that's along the ramp is mg sine theta. Right. So you'll see this, you'll probably see these again. Mg sine theta is the part of gravity along the ramp, and then mg cosine theta is the part of gravity that's perpendicular to the ramp. So you'll see that over and over, but keep in mind that assumes that theta is measured relative to the horizontal. If we called this theta instead, then that would change things. Then these two things would flip. Okay, so be careful about that. Okay, so A is mg cosine theta, or oops, A is mg sine theta, and B is mg cosine theta in magnitude, but keep in mind that it's pointing in the negative y direction. Okay, so maybe a better way to write this is that the x component of the gravitational force is positive mg sine theta, and the gravitational force y component is minus mg cosine theta. Let me give myself some room. FGY is minus mg cosine theta. Okay, so we have our block. We have mg with its two separate components. So on a free body diagram, keep in mind that if you are resolving components, we use a dotted line just to emphasize that these are not two distinct forces. We are taking the gravitational force and just looking at its two components given this coordinate system, x and y. And then we have the normal force and frictional force. Okay, so Newton's second law gives us two different equations. Remember, that's what we talked about the first part of the video. So the x components, so remember, we can analyze things in the x direction and the y direction. The x direction says that mg sine theta, right, that's the positive component of the gravitational force, sorry, the x component of the gravitational force, which is positive mg sine theta, minus the frictional force is equal to max. And then the y directions are saying that n, which is totally in the positive y direction, minus mg cosine theta is equal to may. Now, if we're sure of one thing, if we're going to say that one of these two things is 0, we're sure that the second one is 0, because the block is not levitating all of a sudden. It's not going to start flying in the air, and it's not going to crash into the ramp. Right? Even though it could slide down the ramp, it's going to stay parallel to the ramp. So even though we're allowing for the possibility that ax is non-zero, ay is 0. And you can see from these equations that helps us see that the normal force has to be mg cosine theta. So whether there's friction there or not, the normal force is mg cosine theta. Okay, so that's true no matter what. Now, we can separate this into two cases. So case 1, no friction. So if there's no friction, then lowercase f is 0. and we have AX is, so I'm setting this equal to 0 and then just dividing both sides by lowercase m. So AX would be g sine theta. And then we would be done. So that's not terribly interesting. Case 2, with friction, says that, so in this case we would have to we'd have to be a little bit careful and see whether it's possible for the block to remain stationary or not. Okay, so this is what your book does. So your book has these equations. It talks about the no friction case, AX is g sine theta. And then there's a bunch of words, right? A warning that we should keep variables in. Don't plug in numbers at the beginning. So at the beginning, towards the end of page 60, at the beginning of page 61, your book is talking about, well, if this thing is at rest, it is possible for the thing to remain at rest. And this is the condition. So theta star is a special angle at which the ramp is inclined where the block starts to move. So let's go back to the original setup here. If theta was 0, then the block wouldn't move at all, right? Now imagine theta was like 1 degree. So for most cases of friction, the mass is going to stay on there. Right? So you can keep increasing the angle theta until some limit when the block starts to slide. So your book shows that limit, that special angle of inclination, so they call it theta star, when tangent theta star is equal to mu sub s, that's when it starts sliding. All right. So this is a way to measure a coefficient of static friction, actually. You can just put whatever surface, whatever two surfaces, one surface is your ramp, another surface is some object, and then keep increasing the angle and see where it starts to slip. Take tangent of that angle, that's the coefficient of static friction. All right. So let's assume we have kinetic friction. So assume the thing is moving. We definitely know it's moving. Right? So we're not maybe the angle is big enough that it definitely starts, or someone pushes it at first. So we definitely know the thing is moving. So if we assume kinetic friction, we know the frictional force is kinetic friction, and we can set this equal to mu sub k times the normal force. And we definitely know the normal force is mg cosine theta. So F is equal to mu sub k times the normal force, which is mg cosine theta. So this tells us, so plugging it back into equation 1, plug into equation 1. So it looks like we have mg sine theta minus the frictional force, which is mu sub k mg cosine theta, is equal to max. And dividing by the mass, we get ax is g times sine theta minus mu sub k cosine theta. So you can see that if mu sub k is 0, we just get g sine theta like before. And that's what your book leads up to. So that's equation 4.28 in your book. Looks like we got the same thing. Right? All right, great.